One of the most exciting ideas in searching for exoplanets is to search for planets with magnetospheres. Of course, the Earth is protected by a magnetosphere. Life on Earth wouldn't be the way it is without this protective magnetosphere. But when radiation from the sun hits the magnetosphere, it gives off radio emissions that are theoretically visible. But these wavelengths are very long, and in fact, we've never been able to peer into them. We're blocked here on the surface of the Earth from being able to see them, and no one has ever built a space telescope big enough to be able to observe them. But maybe that's about to change. So my conversation today is with Dr. Mary Knapp, who works at the Haystack Observatory, famously part of the Event Horizon telescope, helping to provide those images of supermassive black holes. And her proposal, and this is the award of a recent NIAC grant, is to launch a constellation of tiny CubeSats that can work together as a gigantic interferometer and to let us peer into these very long radio wavelengths. It'll help us explore and see the universe in different new ways, but also to be able to detect the magnetospheres of exoplanets that would actually be invisible to any of the other methods that we have to detect planets today. So it's a very interesting conversation. Enjoy. What is the Haystack Observatory?
Haystack Observatory is part of MIT, but it is a remote site. So it's where MIT and Lincoln Laboratory have put their radio telescopes to be far from Boston and far from interference. So we are located in Westford, Massachusetts, which is about 20 minutes from Lowell, so northwest of the city. And we have a large site with a lot of very large radio telescopes, including some radars. And we share the site with Lincoln Laboratory, so it's they have defense purposes for some of their telescopes, but we at Haystack, we do basic research. We do science that's open and spans the gamut of radio science.
And what are some famous discoveries that were made using the Haystack Observatory?
Well, one of the projects that is probably the most exciting right now is the Event Horizon Telescope. So currently, the Event Horizon Telescope data that comes in from all over the world is correlated. It's combined at Haystack in a big server room, basically. And that's where the data goes from being ones and zeros and useless on its own to a cohesive whole that can be turned into the really cool black hole images that
yeah. That's cool. All right, so let's talk about your NIAC grant proposal. What's the idea?
The idea is that there's a part of the sky, a part of the electromagnetic spectrum that we've never really seen from the surface of the Earth. And that's because the ionized part of the Earth's atmosphere reflects back very low frequency signals. So we can't see through that layer from the ground. So we need a space telescope. But at low frequencies, you need a really big telescope. So it has been infeasible to date to put a really, really, really big telescope in space to look at this part of the spectrum.
And what size wavelengths are we talking about here?
We're talking about waves that span from about a meter all the way through tens of kilometers. Very, very long waves. In frequency, that is, let's say, 15 megahertz down to 100 kilohertz. So that covers the AM band.
And so, like, even with new powerful radio telescopes, like, say, the Square Kilometer Array, it still can't get you beyond a certain size of wavelength because of the atmosphere.
Correct. Yes.
And is that the line, that 1 meter line? So anything bigger than 1 meter, we just can't see. It's inaccessible from the surface of the Earth?
It varies depending on what the sun is doing and whether it's day or night, but it's between about 1 and 10 megahertz, which is, order 30 meter waves.
Okay, all right. And so then the goal here is to put a space telescope up and, we think about the trials and tribulations of getting the James Webb Space Telescope up. That's a 6.5 meter instrument. How big of a telescope would you need in space? If it was just like one telescope, one big radio dish in space, how big would this thing have to be to start accessing this hidden part of the electromagnetic spectrum?
The resolution of a telescope is the wavelength divided by the diameter of the telescope. So you want your telescope to be many wavelengths across in order to have good resolution. So when we're talking about waves that are tens, hundreds of meters up to kilometers, that's a telescope that's tens, hundreds of kilometers across.
At the very minimum, like if you want
minimum.
so if you want to resolve two wavelengths of a, say, 100-meter wave, you need to have a 200-meter telescope.
Yes.
Right. Yeah.
Which you can see why that is difficult if you think about it as a single dish.
Yeah, sounds a little tricky, but thanks to the power of interferometry, all the work done with the Event Horizon Telescope, break the problem up into little pieces, literally. So what is your strategy for being able to create a telescope that can access these wavelengths?
So we've been inspired by the growth of these commercial mega constellations. They're launching hundreds, thousands of identical spacecraft that are mass produced and therefore less expensive than traditional one-off spacecraft into Earth orbiting constellations for communication purposes. So our thought is, why not take that innovation and apply it to science, to astronomy, and use these economic trends to build a constellation of small spacecraft that will work together as an interferometer and form kind of a virtual telescope that can be hundreds of kilometers across, no problem.
And so how big would each part of the fleet be?
The other innovation that's really driving this possibility is CubeSats, small spacecraft that are the size of a loaf of bread to maybe the size of a big cereal box. So something I can hold in my hand. And that's the size spacecraft that we're thinking about for this constellation, for GOLO.
And I think about, say, the work that's being done on the Square Kilometre Array in Australia, and it is just thousands of these little Christmas tree antennae that work together to provide their portion of the resolution. And so, like, each one of these tiny little instruments, how much, I guess, aperture would they have?
So that's one of the key things that we're going to look at in this study. We're going to look at what antenna maximizes the performance of the array while still being amenable to deployment from a small package. The leading candidate right now is something called a vector sensor, which we're getting ready to fly on another mission in Earth orbit to test it out. A vector sensor is just 6 antennas that are sort of bundled together. And with those 6 antennas, you can measure all of the properties of an electromagnetic wave. There's 6 components, if you want to get into vector math, of an electromagnetic wave. And with the 6 antennas that the vector sensor has, we can measure all 6 of those. And with some advanced signal processing and imaging algorithms, we can turn that information into a relatively coarse map of the sky, just with one antenna. So what we think vector sensors will offer us for GOLO is the maximum amount of information we can possibly collect in a single package. And then we can combine that and make really exquisite maps of the sky. And we are trying out this technology on a mission called AeroVista, which we hope to fly in the next couple of years.
And so then, as you add more of them, what is, do you think, your ideal configuration to maximize your observations? Because I know, like with interferometry, you can increase the baseline, you can increase your resolution, but you don't necessarily get to increase the brightness of the objects that you're observing. That takes more telescopes. What is sort of an ideal configuration, do you think, at this point?
So the really neat thing about a telescope made of many pieces is that you can grow it over time. You don't have to launch everything all at once. You can send more units, more elements on subsequent launches and build up your capacity over time. And the configuration and the number depend on the specific science that one is interested in doing. So there's 2 key factors. There's resolution or sharpness of an image, and there's sensitivity, like what's the dimmest thing that you can see. Mm-hmm. And the the spacing, the size of the array sets the sharpness, just like, bigger telescopes provide sharper images like JWST. And the number, sort of the density, if you like, of elements sets the sensitivity. So for high sensitivity measurements, like, for example, looking for magnetic fields of exoplanets, you need a lot. And part of the study is going to be determining exactly what a lot means, but it's going to be thousands, perhaps hundreds of thousands.
Hundreds of thousands. Wow. Okay. And do you have like a rough sense, like how big would this cloud of thousands or maybe hundreds of thousands of CubeSats together be, like if you just measured it across?
We think that the biggest useful resolution will come from a constellation that's, maybe 1,000 kilometers across.
Right.
So maybe not quite as big as you would think, but it turns out that the plasma that fills the space between stars and galaxies kind of sets a limit on how good your resolution can be. So beyond 1,000, maybe a few thousand kilometers, you'll have diminishing returns in terms of resolution.
Right. So we've got this cloud of thousands, maybe tens of thousands of satellites. Where do you want to put it? Where's a good place to keep this thing stable?
So our leading candidate right now are the fourth and fifth Lagrange points in the Earth-Sun system. And Lagrange points are these special places where there's kind of a low point or a saddle point in the gravitational potential. And the fourth and fifth Lagrange points are behind and ahead of the orbit of the Earth. And they are special because they're stable. They're real dips. They're like a little valley in the potential. So anything you put there tends to stay there. In fact, there's systems of asteroids like the Jovian Trojan asteroids that just kind of sit in these places. So we like those because it's a stable spot. We don't have to use a lot of propulsion to keep our constellation where we want it to be. And we also don't have to worry about cluttering up space. We know that anything we put there will pretty much stay. And if it doesn't, it'll eventually fall into the sun. So it's tidy.
How important is it to keep the spacecraft aligned together? Like, will each little spacecraft have to have its own little propulsion system and try and stay in track, or is it okay if it's kind of rough?
Yeah, it's okay if it's kind of rough. What's important is that we know where they are. So long as we know where they are at any given time, we can make the kind of maps that we're interested in. Each spacecraft will have a little bit of propulsion so that if we want to, we can reconfigure the array for a specific science measurement. There's lots of different configurations one can imagine. And a really cool thing about this concept is you can do that. You can change your telescope to suit the science. So we'll have some propulsion on board for that purpose, to move them around if we want to. Maybe concentrate them in a smaller area, or maybe spread them out just to see what the real limits of our resolution are, for example. Yeah,
I had a chance to visit the Very Long Baseline Array, and they have these giant radio telescopes that are on tracks, and they can extend the telescopes out to the very limit to make a very large interferometer, or they can bring them in very tight if they want to get up like a higher sensitivity on some specific object. And I can sort of imagine that. But I guess you only get so many chances at being able to move them around, and then after a while you run out of propellant and then they're just locked in place.
Right. Another feature, though, is that we can deliver new ones. As spacecraft fail or run out of propulsion, we can send new units.
Does the orientation matter?
For vector sensors, no. The spacecraft could be in whatever orientation they want to be. Vector sensor sees the whole sky all the time. So they can tumble however they want to tumble, and that's okay.
So let's talk about the science that you want to do then. So we've sort of talked about the engineering, about building this giant fleet of spacecraft, putting it at the L4 or L5. What can we do? We've never really observed this realm, so maybe we don't even know. But what do you expect that we'll be able to see in that portion of the electromagnetic spectrum?
So there are a lot of science applications, and I'm not qualified to speak on all of them, but I'll try to give you an overview. the first thing that I am interested in doing is simply making that map. Let's map the sky at relatively high resolution and good sensitivity and see what there is to see. See how the view changes with frequency. See if there's anything that's varying in time, which could be really interesting. And what we'll see immediately is the structure of that plasma that I was talking about that fills the spaces in between stars and galaxies. So the interstellar medium and the intergalactic medium. And we'll see its shape. We'll learn something about the magnetic fields that thread through it. And we'll have, another perspective on our galaxy and on our local neighborhood. What does it look like, and how does it compare to the higher frequency measurements that we've taken from ground-based telescopes and from instruments like the SKA that are coming online. SKA certainly will make exquisite maps at slightly higher frequencies, and we'll be able to see the transition down into lower frequencies with GOLO. So simply mapping and the potential serendipitous discoveries that come from mapping, it's kind of the first thing. When we started looking at the sky in radio waves from the ground, we found pulsars, for example, which was not expected. So who knows what we might find just by making a map.
Yeah, that's interesting. I mean, I think about the first time, X-rays and gamma rays are things that are blocked by the atmosphere. And when they put up the first telescopes and just started making surveys of the sky in these wavelengths we'd never seen before, bright objects appeared, and they ended up being things like black holes and gamma ray bursts and things like that. You don't even know to look for these things, and yet There they are.
Right. So there's real discovery space, I think. And I don't know all that we might see. But there are things that we know to look for. My personal background and field and interests lie with exoplanets. We know that planets in our solar system, like the Earth and Jupiter and Saturn, Uranus and Neptune, they have magnetic fields. And the charged particles in those magnetic fields emit very strongly at these low frequencies. We don't really think about seeing it from the Earth because the ionosphere is in the way and it doesn't come down to the surface where we are. But the Earth is this powerful radio beacon, as are the other solar system planets. And we expect that exoplanets with magnetic fields are going to have the same kind of behavior. And we can measure that radio emission. We'll be able to get a sense for how strong their magnetic fields are, which will tell us about how their atmospheres might evolve with time, whether they're likely to hold on to atmospheres or whether they're likely to lose them. So magnetic fields are a piece of the exoplanet puzzle that we have very few tools for accessing right now. And low frequency radio is, has a lot of potential to help with that, to help us put another piece into that puzzle of how exoplanets work, how they evolve, and ultimately whether or not they may be habitable for life as we understand it.
I mean, we have only one example of life in the universe that we know of that's here on Earth. But we have multiple examples of planets with magnetospheres in the solar system. I mean, we've got Earth, we've got Jupiter, even Ganymede has a magnetosphere, and at different strengths and different levels and so on. So we do have something that we can compare. We know that life probably wouldn't be the same on Earth without that magnetosphere. And so being able to have 3 examples or more here in the solar system, that gives us a really powerful way to compare and contrast other systems in a way that we can't do with life so far, to try and get a sense of this. So how detectable do you think these magnetospheres will be using this array?
They're going to be one of the most challenging targets, because even though planets are powerful radio emitters, they're far away, and they're not as powerful as pulsars, for example. So if they're like the planets in the solar system, which is an if, we don't have much evidence to say one way or the other what exomagnetospheres are like. But if they're like the planets in the solar system, they're going to be dim targets. They're going to be hard, possibly the most challenging target for a telescope like GOLO. So they're one science case that requires a lot of antennas, and exactly how many, as I said, we're going to study and have a much better idea of what we really need and what the best antenna is for the job.
Now, I remember with your proposal, you were suggesting searching out to a certain distance, like a certain number of parsecs. So what kind of, what is your, like, I know this is the whole point of this grant is for you to figure out these answers, but what is your, you must have made some part in your proposal. What do you think is the kind of sphere that we can attempt to detect?
If we're talking about, if we assume that, these exoplanets have magnetic fields similar to the solar system, maybe some of them are closer to their stars than our planets are, something like 10 parsecs.
Right, so about 30 light years.
Yeah, the local neighborhood that we're a part of is what I think is reachable.
And do you have any problem, like with trying to directly image exoplanets? You've got the brightness of the star. It's like, whatever, is it a billion times brighter, the star, compared to the planet? Do you have a similar issue with the intense radio waves coming from the star compared to the radio waves coming from the planet? Is there a coronagraph version in the radio spectrum?
We have a different problem. So we have a much more favorable contrast ratio for low frequency radio. Stars are not anywhere near as bright at these very long wavelengths as they are at optical wavelengths. So our contrast ratio is probably 1 or so, plus or minus a little bit.
Really? Like the brightness of the star is about the same as the brightness of a planet with a magnetosphere?
Yeah. Jupiter outshines the sun at low frequencies often. Not always. It's variable, but sometimes. But stars
really
do
exciting.
emit at low frequencies, and especially when they are experiencing activity, flares and coronal mass ejections. So telling the difference, what's coming from a planet versus what is stellar is definitely a challenge. And there are ways to tell. The time is one of the key ones. Are we seeing variability on a time scale that matches a planet's orbit, for example? Or is it on a time scale that matches the star's rotation? So you can separate out one from the other by looking at periodicity.
Would there be some kind of like signal and response, like the star gives off a burst and then the planet gives off one 8 minutes later?
Yes, quite possibly. We see this in the solar system when there's a strong CME, coronal mass ejection, and it hits a planet. The planet responds, and the radio emission from the planet changes and brightens and changes in frequency. The exact way in which planets respond to the sun is complicated, but there is a response, and that would be the ideal scenario for us to watch a CME leave another star and see another blip as it reaches a planet in that system.
Yeah, or multiple blips as it passes each of the planets with magnetospheres in the system. That's really exciting when I sort of think about that ability. So now, the big challenges with searching for exoplanets today is that you need them to mostly be lined up between us, the star, and the exoplanet, where, the transit method, the planet is passing in front of the star, the radial velocity, it's close to the star. Are there any limitations in terms of orientation in using this technique to find exoplanets?
Yes, but they're a lot less severe than for radial velocity or transit. Radio emission from magnetic fields of planets, it's beamed in a cone, kind of like a pulsar. So it's you think about it like a lighthouse. So as the planet turns, this cone sweeps around. But these cones are wide. So the probability of us intersecting a cone, especially if you take a population of planets rather than just one at a time, is high. So there are geometric effects. Exactly how they work, it's hard to predict because it depends on the geometry of the magnetic field. But sort of on average, we should definitely intersect with some of those cones, even if not every single planet out there.
But these cones they're following the poles of the planet. Like they're going to be going up and down. and going out at some angle that's very wide, and that's almost the opposite of what we see with the transit and the radial velocity method. So in theory, this method could catch the planets that those other techniques would miss. They're catching the ones that are face on, while the other ones are catching the ones that are edge on. So let's say in your perfect world, you launch 10,000 satellites, 100,000, a million satellites, and they are stretched across a field of view at the very limits of what's possible until the interstellar plasma is ruining your results. Are we mapping out the planets, all the planets with magnetospheres in our local environment?
That's the hope. If we have sufficient sensitivity, there'll be some distance limit beyond which we'll only pick up particularly bright emitters, or maybe emission when a CME hits a planet. But within some sphere of, a few parsecs, 5, 10, sort of depends on the sensitivity. Yeah, I think we can pick up all of the planets that have magnetospheres that have favorable orientation for that emission cone to reach us.
And if you had unlimited budget and just kept making a bigger and bigger telescope, is there a limit where no matter how much money you could spend at the problem, you can't resolve any further?
In theory, you can increase your sensitivity by increasing the number of spacecraft. Just go up and up and up and up.
Right, okay.
The limitation is data. It's moving all of that data around and getting it correlated. We have very powerful computers on the ground. It's a lot harder to get them into space and have them work reliably. So the real limiting factor, I think, is going to be data transport and getting it back to Earth.
Is there any value in using both of the Lagrange points, like say use L4 and L5 at the same time to run a baseline between those 2 points?
That's an interesting thought. I suppose if you're looking at something close, where there's not a lot of intervening plasma, potentially even solar system planets, you could have exquisite resolution along that, with that baseline. That baseline is it's between 1 and 2 AU. It's a triangle, so
yeah.
It's a very long baseline, which would give you extraordinary resolution if the plasma didn't ruin it.
Right.
So I'd have to think about that a little bit more to give you a better answer. But that's a neat idea that we hadn't actually talked about yet.
Oh, there we go. The idea that I really like is you put one at L4, one at L5, and then one at L3. The L3 is tricky because it's not gravitationally stable, and so you're going to have to do some work. But maybe you just have like a bigger satellite that sits there and participates somehow. But that you now form this equilateral triangle that is gigantic, as you say. 200 million AU per leg.
Now that I've had a second to think about it, one application for such a long baseline 2-element or 3-element interferometer is solar radio emission. You could track CMEs. They emit at low frequencies as they propagate away from the sun. And you could track them to pretty amazing angular resolution, and as they propagate away from the sun and move out into the solar system and maybe come towards Earth, which is always a concern.
Right.
So
yeah, anything that'll give us a warning of a bad solar storm that's going to take out human civilization would be helpful. What about technosignatures? Are there any kinds of technosignatures that could be detectable in these wavelengths? This is not my field, so I'm going to give my uninformed opinion. Yep.
I would say that's unlikely. If civilization is going to communicate, the sort of information theory says that you have to move to higher and higher frequencies to fit more information into your communication. So assuming electromagnetic spectrum is used for communication, more advanced civilizations would move up in the spectrum, as we have from the very early days of HF communication now to using gigahertz frequencies for cell phones and satellites, and also moving to optical communication. So if we were to see low frequency intelligent signals, it might be like from a very early stage, like, us in the 40s, 50s, 60s. But the energy at these long wavelengths is low, and they spread out. So by the time they would get to us, it'd be extremely faint. And I'm not sure, even with a extremely robust go low, we'd be able to pick them up.
I think this idea, you sort of mentioned this early on in the conversation about building these networks piecemeal, bit by bit by bit, adding more as you go. I think that's a really powerful sort of methodology that could be used across all observatories. I mean, there's some really ideas. You can go. We saw what happened when you spend $10 billion and you take 20 years and you build one exquisite telescope. I would love to see what happens when we spend, $100 million per telescope when we launch them one after the other and they just work together. Do you think that idea has applications across astronomy? Certainly,
their interferometry works at any wavelength. It just gets harder when you go to shorter wavelengths, higher frequencies. So there has been in the past a lot of interest in optical or infrared interferometry for high resolution and for application to exoplanets, actually. And yes, you can launch smaller spacecraft. You just have to work a little bit harder to make them function together as an interferometer. And I hope that we could start at low frequencies where this is relatively easy because the wavelengths are long. And maybe if that's a success, it would bring about the same application of the same technology at increasingly higher frequencies. Certainly there's application for the Event Horizon Telescope to move to space. And there's a lot of work going on around that to increase the baseline length, because right now they're limited by the size of the Earth. And if you want better resolution, you either have to go to higher frequencies or you have to go to space. And which one's harder kind of depends on who you talk to. But yeah, I really hope that, this concept and the study we're going to do will nudge things in that direction.
But even like interferometry is one thing, and as you say, if you're going to try and move into the visible wavelengths, even infrared, you have to get your distance between your telescopes right. It's really tricky work. It's a lot of post-processing. But I think even just putting two telescopes that are a meter across, that were easy to build, easy to launch side by side, not trying to make them be an interferometer, you've got 2 square meters of observing area together. And if you want more telescope, you send 10 more and then 10 more. And after a while, the numbers start to add up and you don't have to necessarily have that precision. Like I like that idea of them just floating around in L4 and you're just taking all the photons that are coming onto them and not stressing about whether or not you've made an interferometer, just that you've added, now it's a 20 meter telescope. Now it's a 40 meter telescope over time.
Right. And you can look in different directions.
Yes.
If you're talking about optical telescopes, there's some really great ideas that are not mine to put observatories at these Lagrange points to look at the sun, to look at asteroids. There are some asteroids that are very hard to see if they are sort of passing between the Earth and the sun. Looking into the sun is hard. So if you were to put an observatory out at these Lagrange points, they would have a different perspective. And if you had more than one, they could look in different directions at the same time. So you get better sky coverage without having to resort to interferometry.
Yeah, I kind of imagine this pipeline of mass-produced, relatively inexpensive telescopes of whatever is the right size, and you're just sending them like we've seen with Starlink. I think this is what caused some of your inspiration, is just keep sending more and more of these telescopes up into some location, and you just make this bigger and bigger observatory. And as you said, they can all work together, or they can all be looking at different targets. But they're relatively inexpensive, because, I mean, this is just, we're moving into my opinion here, but I think, Webb is amazing, but it can only answer very specific, limited questions. And it's sad that we don't have more Hubbles, more telescopes to answer these more general questions. I mean, Hubble's way oversubscribed.
Yeah, there's tons of benefits at multiple wavelengths to being in space. At invisible wavelengths, in infrared, far infrared, in UV, which is a really interesting place to look at stellar activity, for example. So one of my earlier CubeSat projects was a mission called Asteria, which was a little tiny 6 centimeter optical telescope. And we got some really good results just with this tiny little telescope. We were able to pick up exoplanet transits. And I think that something just a little bit bigger, with a little bit more collecting area, would be even more capable. And, I completely agree that the advent of CubeSats and small sats makes this much more feasible to have many sort of mid-sized telescopes in space like we do on the ground. Like there are observatories with meter-class telescopes all over the place, and, they're accessible to students, to researchers without the, factor of 10 over subscription or whatever it is for Hubble and JWST.
But the problem is that we're under this soup of an atmosphere. And so a 10-inch telescope and a 10-meter telescope have roughly they're about the same without any kind of atmospheric correction. Like it's that adaptive optics on the big telescopes that is letting you make the really extreme measurements. But you take a 10-inch telescope and you put it into space, then it's just size is the only thing that matters. You don't need to have that additional adaptive optics operating to get you the better view. And so I think there's like this layer of technology that has to go over top of it. And I'm sure there's some cost balance that I haven't thought through the implications of it, but I'm guessing, we see what's happening with Starlink. We see 60 more satellites. Those could be 60 telescopes going on a single rocket launch and then handed out like candy to astronomers. So
yeah, and it would be a real democratization of access to space telescopes. It takes a lot of work and, really expertise and some, insider knowledge to write and win a proposal for time on Hubble or JWST or any other space-based observatory. And it's still a lottery. It's still a lottery even for the best resourced teams. So,
and I think like when you're doing astronomy, you're saying what is I would love access to Hubble or whatever, but really what is the minimum instrument that I can get my hands on to make my observation? That's what you're looking for. And it may be a 10-inch telescope or something, a meter class telescope at a small university or whatever. If it can make that observation, you're going to try and get time on that as opposed to waiting in line on Hubble.
Right. An exoplanet example, if you wanted to stare at a nearby star, like say Alpha Centauri, just continuously for a year, 2 years, 3 years, just to see if there might be a transit of a relatively far out planet, Hubble's not going to do that and shouldn't do that because that isn't the best use of time. It's very high risk, very low chance of actually finding something, but it would be high impact if you did.
Yeah.
But a smaller telescope could be tasked in a dedicated manner to do an experiment like that. And I think there's probably many other similar examples.
Yeah, I read a paper, it feels like it was about 10 years ago, someone was proposing that we build a small space telescope and its only job is to watch Alpha Centauri.
Yeah,
and it's a terrific idea. I love it.
Yes, that concept has been kicking around. It was originally the motivation for Asteria, and my PhD advisor, Sarah Seeger, was really interested in that at the time.
Right. Yeah. The famous Sarah Seeger. So what's next then? You've won a grant. You have some work to do. What is your deliverable? What are you expecting to produce and when?
So it's a 9-month study. So it's a real sprint. And the end result is a report. And we will report on a couple of key questions. I've talked about a few of them. What's the best antenna? How many do we need? Is L4, L5 definitely the right place to put them? We want to make sure that checks out. We think so, but we want to do the analysis. We'll also be looking at what's the architecture? How would this array be structured? How would it communicate with the Earth? How would it communicate internally? How do we move data? Do we do our data processing in the array on site, or do we send fairly raw data back to Earth and do the processing here, which is most efficient?
I can imagine some kind of mother brain that's out there in the field with them, collecting their data and crunching it and then sending the results home, as opposed to trying to have each separate device send its raw data home.
Right. And that's one of the big architectural trades that we're going to do. We really want to tackle that question. Is it better to have exactly identical elements so that the failure of any one doesn't really matter? Or do you want a heterogeneous array with, larger computation nodes, as you were saying, or maybe larger communication nodes, or maybe those are the same node that's bigger, more powerful. We want to look at that in detail and come up with an answer. Which architecture is better for the kind of telescope we want GOLO to be. I don't know the answer yet, and I'm really excited to work with the team and find out.
Well, me too. I'm really excited about this idea, and I anticipated a bunch of rabbit holes that I'm now going to be diving down, and they have shown up. So now I'm going to be watching this very very interestingly. If you do detect when you start launching satellites, let me know.
Certainly. It's a ways off. NIAC is meant to be early stage, and this is not something that we could start doing tomorrow. But I really believe in this
6-inch satellite. We could do that tomorrow. I think we have that in us.
All
right.
So.
Well, Dr. Knapp, thank you so much for taking the time to chat with me today. Congratulations on the grant, and I look forward to the published paper.
Thank you. Thank you very much for your time.
You can get even more space news in my weekly email newsletter. I send it out every Friday to more than 60,000 people. I write every word, there are no ads, and it's absolutely free. Subscribe at universetoday.com/newsletter. You can also subscribe to the Universe Today podcast. There you can find an audio version of all of our news, interviews, and Q&As, as well as exclusive content that we don't publish anywhere else. Subscribe at universetoday.com/podcast, or search for Universe Today on Apple Podcasts, Spotify, or wherever you get your podcasts. A huge thanks to everyone who supports us on Patreon and helps us stay independent. Thanks to all the interplanetary researchers, the interstellar adventurers, and the galaxy wanderers. And a special thanks to Tim Whalen, Dave Verabioff, Joff Schultz, and Andrew M. Gross, who support us at the Master of the Universe level. All your support means the universe to us.